Hello, my dear student. I'm Mr. Kitwala from Educare TZ. I will be with you in physics for Form 5. So, welcome again to proceed with our discussion about the topic of rotation of a rigid boat. For our subtopic of the talk of a rotating rigid boat. Before we proceed with our discussion here, we were supposed to remember where we ended on the last session. On the last session, my dear student, we tried to see the way we can find the work done by the talk. That is what we discussed on the last session. And we say that always the work done by the torque must be equals to the torque, then we multiply by the angular accelerations. Or we can obtain it by taking the work done might be obtained by taking either the force times the distance, then we times it by the angular acceleration, by the angular displacement. That is what we tried to demonstrate on the last session. We've seen some examples related with what we learned about the work done by the torque. So today here we are going to proceed with our work energy. Now we are going to see the work energy in rotating the object. Imagine we have the rigid body, and that rigid body trying to rotate about an axis. So this object, when it rotating, there are some energy. Could be either lost or could be either gained. That is what we are going to try to demonstrate on our discussion for today here. We have been told that we are supposed to consider a rigged body with the moment of inertia I. Now imagine we have the rigged body, and that rigged body containing the mass, the moment of inertia I. Kwa tuna rigged body ambayo ile rigged body ina a moment of inertia ambao ni I. And we are supposed to let and examine a small regular angular displacement theta from the point to point B. Now we could say that we could assume that this rigged body that have the moment of inertia I containing the small angular displacement. It means that the angular displacement is very, very small from the point A up to the point B. That is why we try to explain here. But my dear student, this is explained into our figure number 23 for our first topic. Now let us jump together so as to see the figure that are trying to explain that when the body rotating, when the rigged body are rotating on and it is an axis, and the angular displacement is assumed to be very, very small. Let us jump together so as to see the figure that trying to explain. As we observe our figure here, this figure gives us the overview about the rigged body with a small displacement. Now we have the rigged body, and this rigged body containing the small displacement as we observe here. And at the point B, we have the tangential force. This is the tangential force that causes this rigged body to proceed rotating about an axis as we try to see here. So this small displacement, this occur between the two radius. The radius 1 that is from 0 to point B, and also the radius 2 which are the same from 0 to the point A. This is where the small displacement occur as we try to observe here. So my dear student, after this one, we can define why the radius is the same. As we know that from the center of the sphere, the sphere or the circular disk having the same radius, because the radius is a distance from the center to any point of the circumference or to any point of the sphere, as we try to demonstrate here. So the work done dw by a torque is moving the object through this small angular displacement the theta. Kwa huyu dw huyu ata represent the work done dw by the torque in moving the object through this small angular displacement the theta is this one. Kwa tutasema sasa kwamba ili tuweze kupata huyu angular displacement, ili tuweze kupata angular displacement for when it is very very small, tutamcall yule work done kwamba small change of the work done must be equals to the torque, then we times by the small change of the angular displacement. This should be our equation number 78 for our fourth topic here. Kwa sasa kwamba ili tuweze kupata small change ambayo the small the energy, it means the work done in energy for rotating the rigged body. Sasa yule small change ya work done atakuwa ni sasa na kuchukua yule toko, alafu baada ya kumchukua yule toko tunamzidishia na small change of the angular displacement. So using the relationship of the torque, if we use the relationship of the torque, we say that the torque is equal. The torque is equals to this moment of inertia. Then we multiply by the angular velocity. Kwa try multiply by the angular acceleration. Lakini angular acceleration ni sawa na nani? Huyu angular acceleration ni sawa na d square theta we divide by dt square, though atakuwa value yake ambapo ni sawa na dw divided by dt. But from the equation number 4.76 we can express the work done as this one. Kwa sasa ukirudi ukiachana na namna ya kutafuta huyu toka ambapo ni sawa na work done ambapo ni sawa na moment of inertia times d square theta, then we divide by dt square. Now we should express with respect to the angular velocity. With respect to the angular velocity tutasema kwamba the second derivative of the angular displacement must be equals to the rate of change of the angular velocity. Kwa ndio maana tumeona hapa kwamba badala ya kuandika dw over dt, badala ya kuandika d square, the second derivative wa yule angular displacement tumeandika ni sawa na first derivative of the angular velocity, as we try to observe here. So from the equation number 56, as we recall from our equation number 56, we can express the work done dw as this one. Kwa tukirejea sasa kwenye equation yetu ya 76 tulisema kuwa tukirejea kwenye equation ya 76 tutaweza kuexpress yule work done ni sawa na small change of the work done equals to the angular velocity to the moment of inertia, then we times by dw divided by dt. How this become, my dear students? How this become? Why we say that the small change of the work done is equals to the moment of inertia times the dw times divided by dt, then we multiply it by the theta. Here, my dear student, our equation, our formula become, because we know that the work done is equal to torque times the angular acceleration. Lakini yule angular acceleration the torque the work done is equal to the work done is equal to the moment of inertia, then we is equal to the torque times the angular displacement. Lakini sasa tumeshaona huyo torque tumeshamdemonstrate tukampata ni sawa na moment of inertia times the first derivative of the angular velocity, as we try. Kwa tukimchukua huyo hapo tukienda kumsubstitute hii equation ndio inakuja. Tutapata sasa kwamba kumbe small change of the angular, the small change of this work done must be equals to the moment of inertia we multiply by the rate of change of the angular velocity, we multiply it by the small change of the angular displacement, as we try to demonstrate here. Now, if we simplify, we should obtain that if we take this the theta divide by the t, tutakachokipata pale tutakuja kupata kuwa kumbe dw atakuwa ni sawasawa na angular momentum na moment of inertia, alafu tuna times by the angular velocity, tuna times na dw, as we try to see here, my dear students.